Good morning, good afternoon, good evening, everybody, and welcome to Wednesday EMinar Day. And today we're going to have a wonderful presentation from Anna Platz on processing strategies. But before we get more to Anna, I just want to remind those of you perhaps that came to this registered for the EMinar a different way, that if you go onto the MTNet webpage, MTNet EMinars, you'll find registration links for all the upcoming EMinars, and also links to the YouTube videos, recordings, and also the presentations of past EMinars. Two more EMinars coming up this month, one next week by Bruce McManus and one the week after by Graham Hill. And coincidentally, both of these recognize some people in EM who unfortunately have passed away recently. The one next week is a tribute to Yves Lamontagne on the University of Toronto EM method, and the one the week after is a tribute to Phil Wanamaker. But today we have Anna Platz on insights into different processing strategies using magnetotelluric data from West Bohemia. And like a lot of us working in noisy environments, Anna's tried a lot of different processing strategies. It's really great to be hearing this. You'll have read Anna's CV, but so I won't read it in detail. But here you can read that she spent since 2014 been a postdoctoral researcher at GFZ, got a PhD in 2018, and is working on pre-stacked data confinement selection and so on in the Emerald code. And our current project deals with efficient data processing for radio MT. So I'm going to stop my share now, Anna, and invite you to start sharing and give us your presentation.
So welcome everyone to this presentation. Today I want to speak about the insights into the different processing strategy or techniques which we used in West Bohemia to improve our magnetotelluric data in this noisy environment. None of the techniques I want to show today is really new. All of them is published and most are really well known and all of these standard tools, but I think it would be interesting to see which of these techniques helped us to improve the transfer function in this area. As I said, there are a lot of man-made noise sources. Most of the processing examples I want to show today are processed by my colleagues Johannes Meyer, Basel Arleit, and also from myself. Our target area was the West Bohemia and also partly the Upper Palatinate. And both regions are located at the border between the Czech Republic and Germany in Europe. The West Bohemia is part of the West Bohemian Massif. And this Bohemian Massif developed between 500 to 250 million years ago. And nowadays, this region consists of 3 different volcanic tectonic units shown in this map here. And we also have the intersection of the Auer Rift, as shown here by these orange colors. And our target area is shown here by this red rectangle. And if you look now on this map, where we see our target area, then we see again these different tectonic units and also the intersection of the Auer Rift, sometimes also called Eger Rift, with a multitude of different fold systems which run more or less perpendicular to this Auer Rift. The Auer Rift is interesting because it is part of a seismically active European Sinusoid rift system and represents its easternmost termination. The entire region is at the moment characterized by ongoing magmatic processes in the intra-continental lithospheric mantle, and first conceptual models are already developed a couple of years ago, as for example shown here by a conceptual model of Breuer et al. And these magmatic processes are similar, for example, to the processes in the Eifel or Massif Central in Europe, or for example, to the processes in the Basin and Range province in the western United States. An interesting fact about these magmatic processes is that they took place in absence of active volcanism at the surface. However, they are expressed by a series of different phenomena. And one of these phenomena is the massive degassing of mantle-derived CO2 in this region. Here we see, for example, a map of the northern part of our study area, and you see all these green crosses which show degassing centers. And degassing centers in our case means mineral springs or mouffettes. Mouffettes are sites of natural cold magmatogene CO2 degassing, as shown in these examples. They can occur as dry mouffette, as shown here, but also as wet mouffette, as shown in these photos. And in the wet mouffette, the gas is transported to the water, and the dissolved CO2 in the water causes an increase in the electrical conductivity. Besides of these massive degassing of CO2, our study region is also famous for repeated earthquake swarms, which are normally located also in the northern part of study area, shown here by this red ellipse. And the seismic energy release in the last 25 years is really focused on this area. Here you see, for example, the local magnitude of these earthquakes in the last couple of years in this region, close to a town called Novi Kostel, shown here on the map. But we have also active tectonics in our region, and this is mainly manifested by Cenozoic volcanism, which is represented by quaternary volcanic structures. For example, we see here the scoria cones of Eisenbühl and Kammerbühl, but we have also some other mass structures in this area, which are all aligned along a fault system running in this direction. And all these phenomena together make this area really a unit target area for European geoscientific research. And therefore also an interdisciplinary drilling program or scientific program was funded by the International Continental Deriving Program called ICDP. And the aim or main aims of this program was to study the physical and chemical processes that led to the magma and fluid transport to the lithosphere and crust, and also to explain the source of these earthquake swarms. Here I show again this conceptual model from Breuer et al., which I showed at the very beginning. And in general, from seismic experiments, we know that we have a lithosphere asteroid boundary upwelling in the study area, as well as an upwelling of the MOHO. And Breuer et al. Postulate that we have also some small-scale fluid or magma reservoirs at the crust mantle boundary, as shown here, and that we have several pathways, fluid pathways from the lower crust up to the surface to the different degassing spots, in our case mineral springs and mouffettes. And the aim of the MT measurements in this area were to map these pathways from the lower crust up to the surface, but also to resolve, if possible, the fluid and magma reservoirs at the lower crust. And for this, we realized 3 larger field campaigns in the last couple of years, starting in 2015. We started in the northern part and then extended it in 2018 to the southern part, but we had also measured as shown here, a small scale grid close to MOFET field. In general, we tried to measure 5 component MT fields for almost all stations in a very broad frequency range from 10 kilohertz up to 1000 seconds. And for this, we normally measure data for 3 days at each station. In all of these field campaigns, we had no really true remote station which we installed for the remote reference testing because at the GFZ we have a permanent remote site which is in Wittstock in northern Germany, and we tried to use this station. So we did not install a remote site during the field campaigns. And in general, we expect that this area is quite noisy, especially of man-made noise, because we have a high settlement density. But we also know, for example, that we have a large power plant in the northern part. We have also a lot of power lines, railway lines. We know of a lot of pipelines. We saw electric fences in the field, but also an active sandpipe or in a dam which is used by turbines. And the first measurements which we did in this area were conducted in 2015 along these 2 perpendicular profiles with 50 kilometers each and more or less 30 stations per profile. The station configuration was realized in order to find the geoelectric strike direction in this area. Because at the beginning, we did not know if, for example, the east-northeast trending overrift or the perpendicular running fault systems are the dominant structure in this area. We found out that we have a geoelectric strike direction in this area, and this is dominated by the overrift. Therefore, Munoz et al. Could run the 2D inversion of the north-south profile, and the result of this model of this 2D inversion was already published in 2018 in Tectonophysics. However, recently, a former master student at GFZ had reprocessed all of these northern data set with new developed tools, but also with a lot more time and different processing techniques. And he was really able to significantly improve the data, which I will show later on some examples. And so we also have now a published 3D model for this northern part. This is published in a master thesis. The second data set, which we measured, were in 2016, and the data points are shown here. Here we really focus on a very small area, only 10 by 5 square kilometers in total. And all these stations are very close to 2 known MOFETs in this area. And the aim was to map directly below the MOFETs the pathways which we expect there. The data of this field campaign is also already not published, but processed. And we did also a 3D model for this local grid. The results will hopefully be published soon in a paper, but also in a PhD phases. And the latest measurements which we did in this area are measured in 2018 along these blue or light blue dots shown here in the southern part. So the aim was to extend the study area more to the south. And we had also some stations between the profiles along quaternary structures, in this case volcanic structures, but also about some faults which are interesting for us. Also, in this case, all data are finished with processing, and the derived 3D model is also already published. And on the next slides, I want to show you a lot of our processing examples in this area and processing techniques which we used, and which of them helped us to improve the data. But first, I want to give you some general comments about the processing which we use. For all 3 data sets, we use the Emerald processing package, which was continuously evolved at the GFZ, and I think first publications are from Ritter et al. 1989 and Beckmann et al. In 2005. But a lot of PhD students, master students contribute to this code, and there are also a lot of further developments in this code. In general, this EMinar3 processing allows you to process your data with a single-site approach, remote reference approach, or for example, a pseudo-remote approach. And it contains a robust routine so that you can apply robust single-site, robust remote reference technique, and all these. And for these robust techniques, there is a robust stacking algorithm, which is described in Ritter et al. And in general, it's based on Hooper and Tuckey weights, and which allow you to downweight or completely remove outliers. Furthermore, the EMinar3 processing consists of a lot of optional pre-stack data selection criteria. I think the most used and most famous one are coherence criterion, phase criterion, Mahalanobis distance criterion, and also the magnetic polarization direction criterion. But we have also a lot of more of these pre-stack selection criteria. Furthermore, we have some tools in EMinar3 to apply notch and delay line filters. We have tools to remove spikes and time series. And we also have a very powerful tool to manually remove outliers, but also noise based on the visual inspection of different physical and statistical parameters. This tool is, for example, explained and described in Beckmann et al. But let us start with some processing examples. In most cases, I will show you today processing examples like this, meaning that you have the apparent resistivity and phase curve of the two off-diagonal impedance tensor components in the period range of 10 kilohertz up to 10,000 seconds. In some cases, I also will show you vertical transfer functions, but in most cases, I focus on impedance today. And the first step, what you normally do in processing your data is first to find time periods which you cannot use in your processing because an instrument is broken, a cable was not connected, or all these other stuff. This is really a very important step, but I will not show it today because this you normally do by looking in time series and all the other stuff. And I will just show you that I have done this for all the stations I will show today. After you remove your data which you cannot use, the second step, what we normally do is to run a robust single-site processing for each station to get a first impression of your data quality for this single stations. And this is shown here for two different stations in the southern part of the study area. I call them station A and station B because I will show you later also processing results for these two stations. And we see that station A has really a poor data quality, and we see a lot of scattered points. In contrast, we see already some parts move curve for station B, which has a much higher quality. However, it is interesting to know that these two stations are only separated by 10 to 15 kilometers. So they are close by. And this shows really that we have a large variety of different noise sources in our study area. And thing what we always or almost always do for our processing is to apply an optional coherence threshold to remove incoherent noise in our data. And for this, in EMinar3, we use the bivariate coherence, which is a value which is normally lies between 0 and 1. And the user has to set a threshold for each transfer function component and also for each station. My personal experience is if you have a station which already has a high data quality, you can choose a really high value close to 1. If you have a station which has a poor data quality, I normally try much lower coherence values. And here you see the results for our station A, which I showed already before. On the left-hand side, we see again our result from the robust single-site processing. In contrast, on the right-hand side, I now also applied, in addition, a coherence threshold, and we see that we get improvements, especially in this frequency range between 100 Hertz and 1 second. As I said, we applied this coherence threshold to almost all our stations, trying different values to find the optimum value for each station. So I can show you the same processing results for station B. Here you see on the left-hand side again our curve from our robust single-site processing, sometimes also called field processing result. On the right-hand side, you see now the result using a coherence threshold. And we get also here for this station some improvements, although they are not so significant as for the station with a poor data quality. Another very important point, what we have to do to improve our data in West Bohemia was to apply several notch filters. And we had to apply these notch filters to remove the monochromatic noise, which come, in our case, from the German railway system, but also from the power grid. Here you see for one time window, the frequency spectrum for one magnetic and one electric channel. And you see that we have some peaks shown here by this yellowish colored, which are coming, as I said, from our German railway system, but also from the 50 Hertz signal from the power grid. And we see that we also have a lot of harmonics. And all these signals disturb our transfer functions. And we have to remove them. And for this, we applied several notch filters using the base frequency and also the harmonics. And for these two frequencies which I show here, we did this for almost all stations. We also had some stations we had to remove other monochromatic noise, for example, with a base frequency of 22.6 Hertz. On the right-hand side, you see now the result of a frequency spectrum after applying these several notch filters. And you see that for these frequencies, which I show here by these yellowish colored, we really could remove these frequencies in our frequency spectrum by the notch filters. And here you see the corresponding processing result for this station as apparent resistivity and phase curve. But in this case, I'll show also the real and imaginary induction vectors. On the left-hand side, you see a robust single-site processing with a coherence threshold. And on the right-hand side, you see the same result, but now applying these notch filters. And you see that in the corresponding frequency range, you get a significant improvement, not only for the impedance tensor, but also, I think, for the vertical transfer function. And I apply these notch filters also for our station A. And on the left-hand side, you see now the best results which we had so far, meaning that we have our robust single-site processing and the coherence threshold. And on the right-hand side, we now also applied the notch filters, in addition to remove the 16.7 and 50 Hertz signal as well as the harmonics. And you see that we really could improve the corresponding frequency range for the apparent resistivity, but also for the phases. And I can show you the same for the station B, which had much higher data quality. Again, on the left-hand side, you see the best results which we had so far, meaning our robust single-site processing using a coherence threshold. And now we apply, in addition, the notch filters before the stacking, and you see that we really could improve these frequency range for between 10 Hertz and up to 1000 Hertz. And not only the apparent resistivity, but also the phase. So this was really a very, very important step for us to improve the data. Another very important tool which we had to use to improve the data in West Bohemia was the Mahalanobis distance criterion. The Mahalanobis distance criterion is also not new. I already published, or I've developed it during my PhD thesis and already published it in 2019 together with Ute. And if you are really interested in this criterion and how it works, I really recommend to read this paper because there are a lot of examples which show in which cases you can get improvements, but there are also the limitations of this criterion explained in this paper. In general, I could say that this criterion is statistically based on an advanced distance measure, in this case, the Mahalanobis distance. And the Mahalanobis distance calculates the distance of each data point to a data distribution, but also considers the shape of a data distribution by using the inverse of the covariance matrix, as shown here by the formula. And if you look what we normally would expect for our data distribution in MT is that we have, or that all events which correspond from the different time windows before the stacking, that they all form one data distribution or one cluster, which is our desired MT signal. And we would expect that we have some noise so that we have some outliers. And this is shown, for example, here on the left-hand side, where we see all the single event transfer functions from the different time windows for one transfer function component in the complex plane, meaning we're showing here the real and here the imaginary part of this transfer function component. And in this case, we have one data distribution, we have some outliers, we have a very, very small noise distribution shown here. But this is more or less the ideal case which would we expect. But in some cases, we have really noisy environments, and the data in these cases also sometimes more complex, as shown here on the right-hand side, because in these cases, we have two data distributions. And in this case, we have our desired MT signal, but we have our also another distribution which is caused by noise. And in this case, we normally would expect that we get really poor transfer function results. The idea of a Mahalanobis distance criterion, which I developed, is to remove outliers like shown here, but also to remove complete noise distributions under some circumstances. And this is a little bit explained here on these figures below. What we normally have is our robust stacking, which we always use to calculate robust transfer function. And during the stacking process, each single event gets a rate between 0 and 1. 1 means that it gets a high or the largest influence in the stacking process, 1 meaning that this event is removed. And in this case, we see that also points which are outliers or which comes from the small noise distribution shown here, get the highest rate of 1, so that they have really a large influence in the stacking process. In contrast, if we apply the Mahalanobis distance criterion before the stacking, only events or data points which are shown here in blue are considered, which are really focused on our data distribution, and which result in much smoother transfer function. If you go now to the right-hand side, where we have this very complex case with a separate noise distribution, then we see what our normally applied robust stacking do is to take data points of both distributions of the desired MT signal, but also of the noise distribution to calculate the transfer function, which also will result in a poor transfer function. In contrast, if we apply the Mahalanobis distance criterion before the stacking, then we only get data points from the larger distribution. Larger distribution means in this case, the data distribution which consists of a majority of events. And in case that this is our desired MT signal, we are able to completely remove the influence of this noise distribution. As I said, if you are interested in this criterion and how it works, please look into my paper. There are also the transfer functions shown for this example here. If we go back to our station A, then we see now on the left-hand side the processing result which we had so far. So we had here the robust single-site processing result using a coherence threshold, but also the notch filters. On the right-hand side, we now apply an addition only the MD criterion using different thresholds for the individual components of impedance tensor. And we see that we get a significant improvement for their apparent resistivity in phases over the entire period range. This can also be shown for a station which has already good data quality, as here for station B. On the left-hand side, you see again our robust single-site processing result using notch filters and a coherence value. On the right-hand side, we see now the result using also the Mahalanobis distance criterion in addition. And also in this case, we get a lot of improvements for the high frequencies, but also for the longer periods, because this criterion is independent of a frequency. Another very important tool which we had to use, especially for the station in the northern part of our study area, is the short-time average, long-time average filter. This tool was originally implemented by Sissi Kütter in 2015 in Emerald, and is also explained in her PhD thesis. In general, the main idea is to compare short-time average time windows with long-time average windows to detect spikes or steps in the time series. And the main idea is, in case if you have not a remote station, to interpolate between the events so that you can move these spikes and steps. And this was really important for us in the northern part, because there we have a lot of pipelines, and these pipelines have so-called current cathodic protection systems, and these causes anti-corrosion pulse noise in our data. You can see this here in the electric channels. We observe then these steps, and in the magnetic channels we observe corresponding spikes. And this anti-corrosion pulse noise is periodically occurring every 15 seconds in our case in West Bohemia, as shown here for a longer time window or longer time series, where you really see the different steps, but also the corresponding spikes. And you also see that we have 15 seconds peak in the frequency spectrum. If we apply this short-time, long-time average filter for our data set, then you see here on the right-hand side that we were able to remove the steps, but also the spikes in the time series. And this is also visible here in the frequency spectrum, because now this peak at these 15 seconds is removed. You see, for example, now a processing result of the vertical transfer functions as real and imaginary induction vectors. On top, you see robust single-site processing using coherence threshold. And on the bottom, you see the same result, but using now this short-time, long-time average filter. A completely independent technique is the pseudo remote processing, but we had also to use this technique at some stations. The pseudo remote processing is more or less a single-site processing technique, but for cases where you have no own magnetic field at a station, because it was not possible to install coils, or coils were broken, the cable was not connected, you use the magnetic fields of a nearby remote station and replace the local magnetic fields with these remote magnetic fields. And then you run more or less a normal single-site processing. And here you see, for example, a processing result of a station where we had no own magnetic fields, because this station was close to a lake, and it was so wet that it was not possible to install coils at this site. I think a more famous, or also a more known technique, is the classical remote reference technique. And as I said at the very beginning of this talk, we could use as a reference station the permanent remote site in Wittstock in northern Germany, which is operated by the GFZ. And the switchstock site shown here has a distance of 300 to 400 kilometers to our station in West Bohemia. On the left-hand side, you see here for a station in the northern part of our study area, the robust single-site processing using a coherence threshold, and you see the apparent resistivity, phase curves, but also the induction vectors. And on the right-hand side, you see now the remote reference result using the Wittstock site in northern Germany as reference station. And you see that you get a lot of improvements, which you also normally expect for the remote reference technique, at least if your noise is not coherent between the two sites. However, sometimes you also wanted to improve the highest frequencies, which go up to 10 kilohertz in our case. And for this, we need a station which is closer to our study area. And also we had the problem that sometimes we have no data from our permanent remote site. And in this case, we tried several combinations of local remote stations. As I said, we had no real remote station installed during the field campaigns, but normally we have 4 to 6 stations which run parallel to each station. So we tried them as combination and to try to improve this. And in this case, I want to show you processing results of 2 stations which were neighboring stations. In this case, meaning they have a distance from only 3 kilometers to each other. On the left-hand side, you see again a robust single-site processing result. In this case, with notch filters and also a coherence threshold. And you see in this case that we get some noise which disturb our highest frequency in the so-called AMT deadband. And with our local remote station, which is only 3 kilometers away, we were able to improve this by the classical remote reference technique. And I think this is also quite good to know that remote station will not always have to be so far away. They could also be very close by. It really depends on the noise which you have in the field. And at least if the noise between the 2 stations is not coherent, you can always use the remote reference technique, even with neighboring stations. If none of the before mentioned techniques worked, then what you normally have to do is to find time periods which contain less noise in the data. And a good starting point in most cases is to separate day and night data. And this we did this for a lot of stations in the northern part of our study area. And in this case, day data means from 8 a.m. to 7 p.m. local time, and night data means from 7 p.m. to 7 a.m. local time. And you see that we get a lot of improvements for the nighttime data. This also shows us that in our case, we really have a lot of man-made noise in the area, which is turned off in the night. So in our case, it was enough to separate this by day and night data. But I know that there also exist more complex cases where you really have to look also for more shorter time periods. And luckily, in our case, these tools or these techniques which I presented were enough to improve all the stations. But we also had this tool which I mentioned at the very beginning from Ute, presented in her paper in 2005, where you have the option to manually remove noise or outliers by visual inspection of physical and statistical parameters. And I also can only recommend this tool because it's really, really helpful to remove noise. However, it is very time consuming because you have to do it manually for each station, for each period, and also for each transfer function component. But as a last option, it would be also worth a try. As I showed you, we tried a lot of different techniques for our different stations. And what we normally get in the end is that we not have only one smooth curve from one processing, but we get a couple of curves as shown here. For example, here you see the nighttime single site processing result. the nighttime remote reference result, the processing result for the short-time, long-time average filter, but also the processing result using the single-site processing together with notch filters and the pre-selection or pre-stack data selection criteria, the remote reference with a local station, but also with the Wittstock station. And what we normally then do is to combine the different processing results to get one smooth curve over the entire, or at least over a lot of our period range, as shown here. And for this, we also have a tool to combine these curves. And the good thing in this case is that you also get a track of which points you get or which frequency you take from each processing results. And to summarize the processing strategy which we used in West Bohemia, I could say in our case, the most important steps were to use notch filters to remove, for example, the 16.7, but also the 50 Hertz signal. It was really helpful to have pre-stacking data selection criteria. In our case, the most helpful criteria were really the coherence threshold and the Mahalanobis distance. And we combined this very often with a remote reference technique, both with a remote station Wittstock, which is 300 to 400 kilometers away, but also with local stations which are close by. And for the northern part, which is more noisier than the southern part, we also had to separate, in some cases, day and night data to improve the longer periods. But at the end of the talk, I also want to show you the models, or the 3 models which we get from our data set after the processing. In general, I could say that we get a lot of high resistivities in all of our models due to the crystalline basement. But our aim was to map these magma fluid reservoirs and the ascending paths for the fluids. And this are normally shown by much lower resistivities values. And this is, for example, shown here. Here you have your stream model of the northern part from using these 2 perpendicular profiles measured in 2015. And in this case, we could resolve one reservoir at the lower crust, and we had more or less 2 ascending paths to the surface. And one of these surface or fluid pathways directly is close or goes close to the surface, where we know that we have several Moffat fields. A similar result we get for the data set from the southern part. In this case, you see only an isosurface, so you see more or less the conductive parts in our model. I could say that we have 2 different small-scale reservoirs at the lower crust, both close to very famous spa resorts called Franzensbad and Marienbad. And we also resolve a lot of these pathways which go from the lower crust up to the surface to the different degassing spots. I show here also the model of a study model of the local grid, which has only this extension of 10 by 5 square kilometers, but which is close to the Moffat fields. And in this case, we really could resolve higher electrical conductivities close to these Moffat fields and to the surface. However, what we not could resolve is different pathways directly below the Moffat fields. In general, you could say that all our 3 models which we derived from the different data sets correspond quite well with each other, and explaining also the data of the other data sets. Here we show a conceptual model which we derived from the 2 original 3D models in the northern and the southern part. And it looks quite similar to the model from Breuer, which we had at the very beginning. We really could resolve some fluid and magma reservoirs at the lower crust. In our case, it were 2, close to Franzensbad and Marienbad. And we also could resolve several pathways which branch close to the surface and goes to the different degassing spots, in our case, the Moffats and mineral springs. And at the end of the talk, I want to show you one more slide with processing results. On the left-hand side, you see again the apparent resistivity and phase curve of our field processing setup for station A, meaning in this case, we have only a robust single-site processing result. And on the right-hand side, you see the final processing result for this station, which had a poor data quality. However, due to our effort and the different techniques which I presented in this talk, we were able to get these significant improvements over a very wide period range. And this is, I think, very important because to get these 3D models, or in general, to get good inversion models, you need transfer function of a good up to high data quality. And as I showed, there exist a lot of tools already. Most of them are standard tools, which could help you to improve your data in noisy environments. However, sometimes a combination of them is required, especially if you have a lot of different noise sources. But I think the most important point is to remember that all the work begins in the field. And if you really want to have high quality transfer functions, it is really important to collect high quality data. And this means that you really have to take your time in the field to collect these data, to collect data where the coils are properly working, where all cables are connected, and to avoid everything which we could not repair in the processing. Because we will have a lot of noise in most of our areas where we measure MT data. So it would be enough to remove these and not also the noise which come into our installation. So please be careful in the field and take your time to really collect high quality data. This is the basis to get high quality transfer functions and in the end to get meaningful models. Yeah, I think I'm finished. Thank you for your attention.
Well, thank you very much, and especially thank you for that huge point about how important it is to do real high quality field work. I mean, I think sometimes people dash out into the field and then they suffer from it, trying to recover from poor field work. And also your second point there is really important, that noise sources vary with time and with frequency. So something that might work at one frequency at one time doesn't work at the same frequency at another time, or doesn't work at a different frequency at the same time. So different techniques really need to be tried. We got a couple of questions in. Please send your questions in. I'll ask the first one, and that is that most of the techniques seem to be frequency independent. But we know there has to be a relationship between neighboring frequencies. In fact, there has to be a Hilbert transform relationship between the real and imaginary parts. And I find that quite a successful approach in order to pick out from, you showed that those clouds. And if you go from one cloud at one frequency, how do you aid choosing in a way that obeys the physics as well as the mathematics, right? Is to try and put more physics into the, have you tried frequency dependent techniques like this?
In our case, no, but I said that the Mahalanobis distance criterion, which I showed, it's statistically based. That's true, but you have to calculate the covariance matrix and also a robust form of a covariance matrix and of the data center. And for this, I use the minimum covariance determinant algorithm. And in this, I really implemented a physical criteria which the neighboring frequency is considered.
Oh,
so
great.
In some part, I brought this point into the statistical criterion. I explained it in my paper, so if someone is really interested in it, he can look at that. But yes, I tried to use it also in this statistical criterion. Because we know that this relationship exists.
Must exist. It must be true.
Yeah.
So the first question is from Malakai Motasai. Sorry if I'm mispronouncing your name, Malaka. What minimum distance do you recommend based on your experience between the reference station and the station being processed when using remote reference processing, or does it depend on the quality of the data?
Good question. I think you have to try it. I normally do broadband MT, meaning that I'm interested in the frequency range of 10 kilohertz up to 1,000 seconds. And for the longer periods, you can really try several hundred of kilometers. And I think it does not really depend on the quality of your station. It's more important about your noise between these two stations.
Yeah, exactly.
And I also tried sometimes remote reference, as I said, here in West Bohemia, they have only 10 kilometers or 20 kilometers, which are separated between the station. And in my case, it was good enough to use this station as a remote station because the noise is not coherent over this distance in this area.
Right.
But if you have an area where you have large resistivities and noise sources which spread over a wide area, then it's difficult. So there is no really rule for this. I only say try it.
Yeah, I would also say it depends on the local geological situation. And in South Africa on the Katwijk Craton, we were seeing correlating DC noise over 300 kilometers. And you don't get that in sedimentary basins, for example.
No.
Okay, the next question is from Lingru Nebera. What are your thoughts regarding using the same remote reference station for data taken from different geological settings? And I guess I kind of just answered that a little bit.
So far, I did not observe any problems with it. I mean, if you look at the West Bohemia and also Wittstock, they both lie in sedimentary basins. Yep. So it's not completely a different setting in this case.
Yeah. Okay, Paulo Rolf asks, says, thank you for your informative talk, Anna. Do you think some of the processing techniques are useful for CSCM, control source CM data processing as well? Have you implemented and tested some of them for CSCM?
Yes, some of these techniques are, I think, helpful for control source EM. And no, at the moment, I haven't tested them. But at the moment, at my current project, I'm working on improving AMT data. And in this case, it would be also interesting to look, for example, at the magnetic polarization direction criterion, which are also developed. So this is my current work to do some of this stuff, yes.
And a question from Venkata Pachigola. Thank you for your wonderful and informative talk, Anna. I would like to know, is this Emerald software package open source or not? I want to do this remote reference processing, and if the station distance is greater than 300 kilometers, can you comment on this?
To the second point, as we already said, try it. It really depends on the noise between the station and also on the period range which you are looking. I mean, if you want to improve the highest frequency, in my case, between 10 kilohertz and 100 hertz, it would be the distance too large. But if you are interested in more longer periods, try it. To the first point, yes, Emerald software package is in general open, but it's not really open source. It's a processing software which we use at GFZ. And it is in general possible to get this code, but I think we have to ask Oliver Ritter and Ute Wettmann, because it's possible to get this code and to use it for process your data, but there is no support. So you have to write your own scripts and all this stuff which you need. I mean, there's always the option to be in contact with one of us, but we have not really the time to really supporting all of these.
Just a quick comment that again in South Africa, for the longer periods greater than about 30, 40, 50 seconds out, we were able to use a remote reference station that was 1,300 kilometers away in order to clean up some noisy data. So it's period dependent. And a comment from Malachi again, is just saying, I asked because my master's is based on processing MT data in the Katwijk Craton. and that processing method can help. And thank you very much.
Yeah, good luck.
Yeah, good luck. Yeah, indeed.
Yeah, I saw some of the data because we also measured some in the Capel Craton some years ago. And as I started as my master student at GFZ, this was one of the first stations which I got to learn the processing. So I know that they are very noisy.
Yeah. Okay, are there any more questions from the audience? No? Well, in that case, I'd like to thank you again, Anna, for an absolutely wonderful presentation. And this presentation will be available in a few hours on YouTube. And Anna's already sent me a PDF of the presentation, and I'll be putting that up on MTNet. So thanks again, Anna, and goodbye, everybody. See you next week.
Goodbye.